Okay, so this is week 10. Okay, and today I'm going to continue on design of transmission shaft, and then we're going to look into principal stresses in beams under combined loading. Okay, so yeah, it depends on how much we can do. Principal stresses in beams under combined loading might not get there, but anyway, there will be a tutorial held on July the 8th at 7 p.m. And I know that some of you have a term test to attend. You go ahead. The tutorial will be recorded. Quiz 7 will be held on July 9th. So this will be on a Friday. Okay, this is on a Friday because some of you have a term test. Okay, you cannot do it on a Thursday. Then the quizzes for everyone will be moved to a Friday then. Okay, any question, anyone so far? No? Okay,
Sir,
so, yep.
I'm sorry, I just joined. So is the quiz going to be moved to Friday this week?
Yeah.
Oh, okay.
Okay, will be moved because some students are taking fluid mechanics and they're having a test on that day.
Okay. All right.
Okay.
All right. Thank you.
But there will be a tutorial. Okay, but if you cannot attend the tutorial, it's recorded. You'll be fine. Okay.
All right. Thank you.
Okay. So let's briefly look what happened last week. Okay. So last week we look into design of a transmission shaft. Okay. So this shaft will be having a loading of P, Z, P, Y. It can also have a load of axial load and then a torque. Okay. Now I want you to take note that not necessarily our analysis today will take into consideration the axial load, but in reality, they can be axial loading. Okay. Then we design the shaft. Okay. We look into an element. Okay. So just briefly recap, we look at an element over there and we started drawing the stresses on the element, and this is our outcome. Okay, and then we did 3D mold circle to ensure, right, to ensure that the XY exact plane, okay, is the biggest circle. Okay. Later on, when we do 3D mold circle, I'll go more detail into here. But for a shaft, it's definitely that the element on the surface will have the largest diameter. Okay. Some of you will ask me why is that? Because there's only one normal stress component and one shearing stress component. Okay. So when you construct mold circle, you will get the one I'm highlighting now, the biggest circle. Okay. You will not get the smaller circle like this. You will not get these two circles. Okay. Right. So from here, we draw an element, right? Then we look into the stress average, which is equal to stress x plus stress z divided by 2. And then we realize that over here, where we have our stress x divided by 2, we call it also equal to uh, stress m divided by 2, where stress m, okay, watch this, this is important, okay? Stresses induced by the moment when the shaft is not under what? Axial loading. Okay, so this one, we are focusing on the shaft that's having a torque and a moment without axial loading. Okay, and where we last stop at the radius of the circuit. So I'm going to write out, or I'm going to cut and paste this entire term over here, okay, to our today's lecture. Okay, so to our today's lecture. Okay, so this is a continue of design of transmission shaft. Right? So we realize that tau max, the radius of the circle, which is equal to tau max, is equal to stress average plus by tau xy squared. Right? Now, the thing now is how, right? How to obtain or how and why tau max, okay, is so critical or is critical. Okay. So let's look at how first. Okay. So how, the tau max, right? Tau max can be acquired from uni Excel tensile test, or pure shearing test. Okay. So if you look into our material property, right? A while ago, I wonder was it last week? We look at material property, right? We look at here. All right, we have this property. I'm going to copy. All right. So I keep on highlighting this table, okay, because this is a material handbook table, or properties can be from any handbook. Okay, so this is what I see. Excuse me. So what you realize that not always, unfortunately, okay, not always you have the shearing use stress. Okay, so if you look at this table, you only have one, okay, at 145, and then you have 1 over 150. So if you don't have that value, what are you going to do, right? So we know that this is done through uniaxial compression tensile test. And this is done by pure shear. So pure shear, what do I mean is they have a shaft. This is your test specimen, right? You induce a torsion, okay, and then you measure the stresses, okay. But it is not as common as tensile test, right? So what can you do, right? The thing now is what can you do to let's say you want to use a steel, right? That is over here. There is a quench tempered steel, right? But you don't have that value, right? You only have a tensile test data, right? What can you actually do? Okay. So I'm going to teach you now, right? If you are not given the shearing test, right? You only have tensile test. This is what you could do, right? So if we draw, if I will go into a different view, right? So I'm going to draw. So this is my X. This is my Y. And this is my Z. Now if now we have a shaft, right? And then this shaft that I've just drawn is under unit axle tensile test. Okay. So here P, you have the other couple, P prime. Okay. So if I were to put an element, okay, we were to put an element, right? Put an element over there. Then if I were to draw, okay, if I were to draw the element, okay, so I'm sorry, I think this element I should have drawn this way. I do apologize. Maybe it's not so obvious, but I'm going to put the element over here, right? So if now I were to draw the element, right, and draw the element, so I'm going to draw this. I'm going to draw by the side so you can see. So now this is my X, this is my Y, and this is my Z. Okay, so this is our element now. So our element is only under stresses in the X direction. So this is stress X, right? And then that's it. We don't have any other loading. Okay. So if you look at this element over here, if I were to label this, this is my point X, point Y, and then point Z, right? So now we can say that stress X is positive, while stress Y and stress Z is equal to 0, and all the shear component, right, equal to shear XZ is equal to shear ZX is equal to shear YZ is equal to shear ZY. All of them are equal to 0. Okay, there's no shear at all. Okay, so when that's the case, when we start constructing mold circle now, right, we start constructing 3D mold circle. So this is your X. Why do I construct 3D mold circle? Is in real life, right? The mold circle is in 3D. The element is always in 3D. Okay, 2D is just learning concept. Fine, you understand the concept. 3D is more on real world application. Okay, so this is your normal stress, and then you have your shearing stress. Element rotate clockwise, element rotate anti-clockwise, and then we know, right, stress Y and stress Z are on the shear line, and then we are also aware that this will be our stress X, right? So for this case, this is our point X, and you can see this for the first time, that a 3D mold circle can be a single circle in this condition, right? So this is your point Y and also your point what? Or point Z. Okay. So now we can start constructing our mold circle from here. So this is our mold circle, right? So what you realize, what we have what we have quoted over here, the distance from here to here, right? This distance from here to here. This is our stress U, right? When we test